Welcome to lesson 4. You should have already completed lesson 3, which was a booklet of past paper questions on basic Born-Haber cycles. So we're going to move on to lesson 4 now. Lesson 4, it's just going to tie up quite a few things. We've done the bulk of the work. We just need to basically draw together just a few more concepts that, oddly enough, even though it's about maybe 15% of the work that we need to cover, it's actually going to get you quite a few marks, much more marks than 15% for this topic. Anyway, you should have done lesson 3. If you have any problems with lesson 3 or with what you see on this video, as it says there, just get in touch. So what you should already know, blah, 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 you should know all your definitions, obviously, from lesson 1. You should be able to construct the Born-Haber cycle from scratch. So literally, if you're given the name of an ionic compound, you should be able to produce all the stages in a Born-Haber cycle. And then you should be able to calculate any enthalpy value. So it's the usual thing, you know, you've got 6 or 7 values to consider. They will give you 5 or 6 and you have to work out the unknown. It's relatively straightforward. Again, if you don't know how to do that, you need to get in touch. So the first thing we need to consider is the enthalpy of solution. This is fairly straightforward. We just need to think about the enthalpy of solution. So dissolving an ionic compound in roughly 3 stages. It's split into 2, but we'll look at it in 3 stages. So the first thing we need to do is break up a lattice. So this is dissociation. So the enthalpy of lattice dissociation we need to consider. So anytime we break something up, we're putting energy in, so it's endothermic. And then there is hydration. So this we look at it later, but this is basically the attraction of the positive ions to water, and also the negative ions to water. So in our ionic compound, which contains positive and negative ions, we break that up, and then the positive ions are attracted to one part of the water molecule, the negative ions are attracted to another part of the water molecule. And when we get that attraction, either the positive ions or the negative ions of the water, when we get that attraction, it's bond making, so that is obviously exothermic. So what we've got to do is we've got to break up the lattice. So we've got a lattice there, it's very simple, sodium chloride lattice. We can chuck it into some water, and what will happen is that we will break those ionic bonds that are forming the lattice. So when they break, the ions go into solution. And in solution, what we've got to remember is that the water molecules are polar. So here it says energy must be put in to break the bonds in the giant ionic lattice. It's endothermic, we've already covered that. So with our polar water molecule, and you can see there slightly negative for the oxygen, slightly positive for the hydrogen. You should know why that molecule is polar. It's the difference in electronegativities of the atoms involved. So you have a molecule that has a slightly positive side, a slightly negative side. So that's why we've got that polarity in the molecule. So when we consider the hydration of the positive ions, so we're going to form bonds between the positive ions and the water molecule. Forming bonds is exothermic, there's attraction involved. So what happens is the positive ions are surrounded by the water molecules, and they're obviously surrounded by the slightly negative end of the water molecule. So that attraction is going to be exothermic, so energy will be released. So we also need to consider the enthalpy of hydration for the negative ions. So what we can see is that we've got our water molecule. Again, it's polar, we know why it's polar. But the water molecules orientate themselves around the negative ion with the slightly positive end. So the hydrogen atoms are attracted to the negative ion. So that's fairly straightforward. However, we still got attraction, so it's still bond making, so it's still an exothermic process. So what we need to consider is this equation, and all of the marks essentially are driven from this equation, and it's relatively straightforward. So we've got our enthalpy of solution, which sometimes you're asked to calculate. We've got lattice association. We've got hydration of positive ions and hydration of negative ions. So we've got an overall enthalpy of solution, an endothermic lattice dissociation, and an exothermic hydration of positive ions and an exothermic hydration of negative ions. So you've got possibly 4 things. You would be given 3, and you would need to calculate the 4th. And it's just really simple maths. So we're going to move on to perfect ionic model. So this is the theoretical model. So again, this can seem quite complicated. You can get bogged down in it. There's 2 ways you can look at it. You can try and understand the theory, which isn't particularly complicated. It's just the fact that you could get tied up in definitions if you're not careful. If you don't want to sort of waste too much time, if you're getting bogged down with the theory, you can just remember a couple of things which I'll discuss later on. Anyway, what we've got is that we've got a theoretical lattice. So the theoretical lattice is what physicists use for some reason. So the physicists are using a completely theoretical lattice enthalpy, and they are assuming that we've got a perfect ionic model. So this is in theory, in a perfect world almost, that we've got 100% ionic bonding. Smart students would actually look at that statement and think, if they assume that we've got 100% ionic bonding, then there are situations where you don't have 100% ionic bonding, and we'll cover that in a minute. But as soon as you mention that you've got an assumption that there's 100%, it leaves the door open for the idea that, well, there are situations where we don't have 100% ionic bonding. Again, assumption that we've got perfect spheres, so perfectly round shapes. Again, if they're assuming that, it does leave the door open to suggest that there are ionic models, well, not ionic models, there are ionic lattices where the ions aren't perfectly spherical. Point charges, the charge is concentrated in the center of the ion. So let's have a look. That's what that would look like. So literally all the charge is right in the middle. Now I wouldn't get too concerned about these. Really in the A-level questions that you see, you will be given the opportunity to mention something that the perfect ionic model relies on, and usually it's only looking for one of these. So pick your favorite one: 100% ionic bonding, or no covalent characteristics, perfect spheres or non-perfect spheres, so just pick one or 2, and your understanding is not necessarily tested in terms of explanation. Usually you just have to recall this. So we've got the opportunity for all the students to pick up plenty of marks on this. So no covalent bonding or no covalent characteristics, we'll cover that again now. We'll look at that. So we've got a theoretical versus experimental. So the theoretical is just based purely on assumptions, on sorts of calculations that the physics boffins are doing, and the experimental values are the ones that we get from the Born-Haber cycle. So the Born-Haber cycle is where you would conduct a series of experiments and calculate a lattice enthalpy value. So similar to what you've been doing on paper with the practice questions and in the lessons previously. So the main thing to remember, Born-Haber cycles are experimental. So this is what we can work out in the lab. The Born-Haber cycles are greater than the theoretical value. They'll either be equal to, if you happen to have an ionic compound that you're experimenting on. If you happen to have an ionic compound that is a perfect ionic compound, i.e. 100% ionic bonding, no covalent bonding, all perfectly spherical, all point charges. So it would either be equal to or it's going to be greater than. Now the good news is that if you're asked to comment in an exam on whether the value for the experimental Born-Haber cycle is going to be less than, equal to or greater than, you can say pretty much in all cases it's either going to be equal to or greater than. Anyway, we can move on. So with Born-Haber cycle, it's going to be greater than or equal to the theoretical value. We have extra bonding due to covalent characteristics, so that's why the lattice value is going to be greater than the theoretical value, because the theoretical value just assumes that it's 100% ionic bonding, where in actual fact a lot of ionic compounds will have additional covalent bonding, and if you've got ionic bonding plus the covalent bonding, the lattice enthalpy will be greater because you're going to have to put more energy in to overcome not just the ionic bonding that the theoretical model assumes, but you've also got a dollop of covalent bonding in there, so you would have to put in additional energy for the actual covalent bonding that exists. Okay. The main thing to remember here, and you can take this away again if you get bogged down in the theory, you should have been able to look at the theory that I've given for the notes for this lesson. But the main thing is that if you've got a difference between the Born-Haber cycle experimental values and the theoretical values, any difference is due to covalent characteristics, i.e. it's not perfectly ionic. And the rule, sort of general rule that we can apply, is that the greater the difference between the experimental and theoretical means the greater the amount of covalent bonding or covalent characteristic. So it's fairly straightforward. We need to have a quick look at this idea of covalent characteristics, how the covalent characteristics sort of appear in the ionic compound. So what I've got on the slide, we can see that we've got an ionic compound on the left and a covalent compound on the right. And most students sort of see these possibly as opposites, as being sort of opposite forms of bonding. Well, they're just sort of extreme forms of the same bonding, where we've got the idea of electrons being either lost or gained with ionic bonding or shared with covalent bonding. Well, you can actually have a blend of the two. You need the right type of atoms involved in the bond to have a blend of the two, but you can essentially have, and you've seen this already. So what I mean by this, if we take the covalent molecule, as soon as we've got a difference in electronegativity, so we've got an oxygen and a hydrogen, as soon as we've got a difference in electronegativity in the molecule, we can have partial charges, and we know about this, we've seen this before. So we know that this molecule is polar, and we know that it's polar because the more electronegative oxygen is withdrawing electrons from the electron cloud. You only actually get pure covalent bonding when you've got a molecule that contains identical atoms, or a bond that contains identical atoms. So where there's no difference in electronegativity. So here we've got fluorine molecule, so two fluorine atoms, no difference in electronegativity, so the electron cloud is dispersed evenly. So there are no partially negative or partially positive ends to that. So that's the only time you'll get the pure covalent bonding. Anytime we get the difference in electronegativity with the atoms, as in the water molecule, the electron cloud is skewed. We've seen this before, so we get the electron deficient hydrogen atoms slightly positive, and the electron rich oxygen atoms which are going to be slightly negative. So all we've got is a sliding scale, really, going from ionic to covalent, but it's essentially the same sort of bonding. So in this compound we could have covalent characteristics, but it depends on the type of atoms involved. So what we've got is the idea that if we've got the right sort of ions, we can have an overlap of electrons. So it's similar to our covalent bonding that we know about. But we've got to have the correct sort of ions involved, and you can see there we've got a very small positive ion and a large negative ion. So that would do for most students' understanding. So a small positive ion, like maybe like a lithium ion, and a large negative ion, like maybe iodide. So what we've got to think about, the smaller positive ion, it can get in closer, it's got a positive charge. Because it's small, we've got that greater charge density. So small positive ions pack a greater punch. And then a larger negative ion, it's easier to withdraw or attract the electrons from the outer shell of a large negative ion, basically because the outer electrons are further away from the nucleus, so they're not held as tightly. And what that will do is allow us to get some sort of covalent characteristic, because some of the electrons are going to be sort of shared between the positive ion. And that's basically it for lesson 4. Nice short one. So what you need to do is go away, have a break, complete the AFL lesson, which is an online assessment. I'll have a look over that when you've completed it. And again, if you've got any questions with any of the content that we've looked at in this video or in the AFL lesson, which is your next lesson, lesson 5, just get in touch.